Hello. Inspired by Ben Eder's fantastic video series about building an 8-bit computer completely on breadboards, I built my own version. In this video I want to talk about the registers and the ALU, which is some kind of heart of the computer because this is where the real calculations are done. A register is just an 8-bit storage for a single byte in my build. That storage is connected through 8 data lines with the data bus, and I have 8 LEDs that show the current constant of that register. I use a register chip HCT 377 that is capable of storing these 8 bits. It has a clock line that allows a synchronous load of the data on the rising edge. Also has an enable line that allows the chip to be disabled so that it does not load the data even if the clock ticks. And it has separate input and output lines. These input-output lines are unfortunately not on one side of the chip, but they are mixed up in both sides so that it's not too easy to wire the chip up. Also, that chip does not have an output enable pin, so I have to use an additional bus transceiver, an HCT 245, to connect that bus to the chip. The schematic for the register is as simple as the register itself. So there is the outer world, let's say. This is the connection to the data bus here on the lower side, which is connected to the input pins of the 377 and connected to the output pins of the bus transceiver. And there is the internal side, which is connected to the output bits of the 377 and connected to the LEDs on one side and to the bus transceiver on the other side. The control lines for enabling, for outputting, just go to the bus transceiver, and the right enable, which is reading the data from the data bus, is connected directly to the 377. This is the board with the register. The register chip is here, and that stores the register value, which is shown with these red LEDs here on the right hand side, and that bus transceiver connects the register to the data bus. In fact, I have in total 4 of those registers, and each register needs one board to hold the circuit. The ALU does all the arithmetic and logical operations in my CPU. It starts with addition and subtracting, or with shifting data like multiplying or dividing, and there might be some other calculations that are done by the ALU. It also does some logic combinations like the classical and or not, all those bool operations, and some more like XOR. The input to the ALU are the left-hand side and the right-hand side, so there are 2 values that go into the ALU, and there is a function that describes the operation that has to be done by the ALU. The output of the ALU is first of all the result, so that is the combined value of the left-hand side and the right-hand side, and there are some flags that leave the ALU and that are also stored, so that you can use those flags to later select certain operations or functions depending on the state of flags. There are several ways how input and output is provided to the ALU and how the result of an operation in the ALU is stored. One way is the fixed registers way. That is the way that Ben Eder used in his SAP build. That means the first value is always one register, maybe register A, and the second value is always another fixed register. In this case of Benita's CPU, it's the register B. And the result is always put out on the data bus so that another register or one of those registers can fetch the value that is the result value. Another option is to use additional buses. That is the way that James Sharman uses in his CPU build. So you set up two additional buses, a left-hand side bus and a right-hand side bus. And the first value is always taken from the left-hand side bus, and any of the registers is eligible of outputting its current content to the left-hand side bus. So any of the registers can be the left-hand side of the ALU operation. The same is for the second value. You use the right-hand side bus, and any register is capable of putting its current content on the right-hand side bus, which in turn is the second value for the ALU. And the result then is put out on the data bus so that any register is capable of fetching the value from the data bus. That altogether means that you have great flexibility. You can put any register to any side of the ALU as input, and you can fetch the result into any register with just one single CPU cycle. On the other hand, you need a lot of additional wires for the left-hand side bus and the right-hand side bus, and you need additional bus transceivers to isolate the current state of the registers from the buses. Another variant is the one that I chose. That means you have an additional register. In my case, I call it the ALU register, or sometimes it's called Accumulator. And is an additional register that can be fed from the data bus or that can provide its value to the data bus. And this is always the first value for all ALU operations. So the left-hand side of the ALU is always taken from the ALU register. The second value is taken from the data bus, so any register that has a connection to the data bus can provide the second value. And the result of the ALU operation is stored in the ALU register, again overriding the old input to the ALU operation. That value from the ALU register then can be put on the data bus on the next cycle and can be fetched by any of the registers. This setup provides the same flexibility that you have with the additional buses, using a lot less hardware, but on the other hand, it's much slower than the other two variants, because you always have to put the first operand in the ALU register in one cycle, and then after the operation you have to transfer the value from the ALU register to the destination register. The first part of the schematic shows the internal register of the ALU, which has great similarity to the register schematic that I showed you before. There is a 377 that holds the current state of the ALU and that has a direct connection to the bus transceiver 245, which in turn has a connection to the data bus here on the left-hand side. There is also a connection through this bus to the ALU chips that are further down in the schematic and that I will show you in a few minutes. The input of the 377, however, is connected to those multiplexer chips on the right-hand side that I will also show you later, and it is not directly connected to the data bus. What is not drawn on the schematic are these 8 LEDs that show the current state of the 377, but those are the red LEDs on the breadboard. The heart of my ALU is that ALU chip LS382 that provides the basic operations for arithmetic and logic. This is a 4-bit chip, so I need 2 of them to build an 8-bit CPU or ALU. The available functions of that chip include things like adding and subtracting and XOR and AND. It also has 2 constants that can be loaded, 0 and 255, which come in handy later. My goal was to have all basic arithmetic and logic calculations, so I wanted to have addition, and that is available on that chip. Also subtraction is available, and even multiply by 2 can be accomplished with that chip, although it has no specified function for that, but adding the same value to itself, a plus a is the same as multiplying by 2, so it's the same as left shift. But it has no right shift capability. It is not able to divide a number by 2. For the logic combinations, you have the add, OR, and XOR functions available, and also the NOT function is available by XORing the input value with a fixed value of 255, which can be provided by the chip. For the flags that I wanted to have, you see the carry, so the over or underflow of an addition or subtraction is available. There is no 0 indicator on the chip, but it has a negative indicator, so the negative indicator of course is trivial, as you only have to pick up bit 7 of the result, which is always the negative bit. For all those functions that are not provided by the 382, I added an additional control line that I call CS, or special command line. So to select the real input to my ALU register, I use 4 HCT 153 multiplexers, which are 4-to-1 multiplexers, and those multiplexers are wired that way that if the selector is 0, the ALU register takes the output from the ALU chips. So this is the classical normal operation, that the result of an operation is fed into the ALU register. If the selector is 1, the data for the ALU register is taken directly from the data bus, and so it is possible to load the first operand into the ALU register over the data bus through this multiplexer. Then there is the left shift operation. That means that the data is taken from the data bus, but the bits are shifted 1 to the left, so bit 0 from the data bus becomes bit 1 in the ALU register, bit 1 from the data bus becomes bit 2 and the result, and so on. And even the C flag is incorporated in that shifting in a way that the C flag old value becomes bit 0, so the rightmost bit of the result, and bit 7 from the data bus is shifted into the C flag, so that the new C flag is taken from the bit 7 of the data bus. The last possibility on the multiplexer, value 3, means right shift from the data bus. So the same way that we shifted left in the function 2, we shift to the right on function 3, that means it's dividing by 2. So bit 7 from the data bus becomes bit 6 in the ALU register, bit 6 on the data bus becomes bit 5 on the data bus, and the C flag is incorporated in a similar fashion. So the old value of the C flag becomes the new bit 7 on the result, and the bit 0 on the data bus becomes the new C flag. That way, shifting to the right or dividing by 2 is done just by wiring the data bus into the multiplexer and selecting the shift operation. This section of the schematic shows the part of the ALU where the real calculations happen, which is done mostly by those two 382 ALU chips. The functions are selected by the selector lines, which are drawn here on the left-hand side, and which select the function directly by switching between the 8 available functions of the 382. The fourth line is for special functions which are not handled by the ALU chips directly. The input to the ALU chips come from the 377, so the internal state of the ALU on the one hand, and directly from the data bus on the other hand. The output of the ALU chip is fed into those multiplexer chips that handle all those functions of the ALU which are not included in these 382 chips, mostly the shift functions, shift to the left and shift to the right, and the direct load from the data bus. The output of the multiplexer chips then is fed into the 377 so that the internal register can be updated. So in my ALU build I have those 4 flags. First, the carry bit, that is the over or underflow flag for addition or subtraction. Then there is the 0 flag that shows that the result is completely 0. There is that negative flag that shows that the result bit 7 is set. And there is an overflow flag that shows that in 2 complements arithmetic the sign changed. The source for the flags are mostly my ALU chip, that LS382. The carry is provided at pin CN+4. The negative is provided on pin F3, which is the highest output bit. And the overflow bit is provided at pin OVR. Only the 0 flag is not generated by the 382, so I have built my own logic. It consists of 2 4-input NOR gates, that is a chip called HCT 4002, and there are 2 4-input NOR gates on the die. And you see, if all bits on the NOR gates are 0, and only if all 4 bits on the input are 0, then the output is 1. As soon as one of the input bits is 1, the output becomes 0. And so the first 4 bits are connected to the first gate, and the last 4 bits are connected to the second gate. And if you AND that together with an additional AND gate, an HCT 08, you see that the output of the AND gate is 1 exactly if all of the input bits are 0, and that is my logic for calculating the 0 flag. All the flags of my ALU are stored in a 4-bit register. It is that well-known 74 HCT 173 4-bit register chip. So the carry flag, the zero flag, negative flag, and overflow flag are stored in that chip. That chip is directly connected to my instruction decoder logic in a way that the jump table that is stored in the flash ROMs points to different locations depending on the flags which is used for conditional jumps or for some other specific instructions. On the other hand, there is a connection to the data bus through a bus transceiver. It is that HCT 254, and I use that to push or pull the flag state to the stacks so that I can take the current state of the flags and push that to the flag and restore it later. This is used explicitly with those PSF or the push flag or pull flag instructions, and it's used by the interrupt handler that is capable of saving the flag state during an interrupt, and also the interrupt inhibit flag is passed through since the HCT 254 is an 8-bit bus transceiver, but I only have a 4-bit register chip. There are 4 bits free, and I wire the interrupt inhibit flag to the 254 on the flag register, so I can put the interrupt inhibit flag to the data bus through this bus transceiver on the ALU. This part shows where the flags are stored. It is this 74 HCT 173 chip that has the 4 bits for the flags, and the inner side, the values of the flags are fed through those lines through to the instruction decoder. But the flags can also be put on the data bus through this bus transceiver here, and the flags are put on the data bus to be pushed on the stack, and they can also be read back later. But additionally to the 4 flags from the ALU, there's one additional flag that comes from the instruction decoder, and it is the interrupt inhibit bit that is also put on the bus through this transceiver, and so this allows for storing and restoring the interrupt inhibit state. Some special treatment is necessary for the C flag, since the C flag is used during additions and subtractions. I need special commands to either clear the C flag explicitly or set the C flag explicitly. Clearing the C flag is necessary before an addition, and setting the C flag is necessary before a subtraction. It can also be used to shift in or shift out a C flag during the shift operations. So there is a dedicated ALU control set that allows manipulating the C flag without disturbing the other flags. So there is an additional multiplexer. It is that HCT 157 that allows a single selector and 4 inputs. And whenever there is normal operations, all flags change depending on the ALU result. That means that all flags, including the C flag, are controlled by the ALU chip. And there is another option that allows a special C flag handling, and that means the C flag value is taken from the instruction. So depending on if it's a clear C flag or a set C flag instruction, the C flag value is taken from that instruction. And all the other flags keep their value so that those flags do not change during C flag handling. This section shows the logic for the flag input, because the input of the flags changes with the ALU function. And these 2 multiplexes select depending on the ALU function, and it is the first stage of the input for the flags. So in case of a simple ALU function like calculating with those ALU chips, the flag input is taken directly from the 382. In case of one of the shift functions, the flag is taken from whatever source is right. For the C flag, it is the data bus, because the data on the data bus is shifted, and so it is either the lowest or the highest bit which becomes the C flag. And the C flag is also taken from the bus as long as the bus read is selected. The other flags are respectively, so for the 0 flag, it is always taken from the 0 flag logic, either for the simple functions as well for the shift functions, but not in case of a read from the data bus. So when the flag register is restored from the stack, the 0 flag is read from the data bus. The second stage is about the C flag. So there is another multiplexer that is just 2 different stages, and when the C flag shall be changed, the selector for the C flag is set, and the C flag is taken from the control line 0, and all the other flags are taken from the register. So the complete overview of all the ALU and flag functions that are provided by my ALU include these 16 variations, while 3 of those are unused. The first 8 just mirror the 8 operations that the AS382 provides, and whenever there is an A, that means the input is from the data bus. Whenever there is a B, that means it is the ALU register that provides that value, and the result is always stored in the ALU register. The last 8 operations are provided by this extra special command bit, and includes things like loading the ALU value from the data bus, left and right shifting, or all those C flag manipulation operations. These 4 bolts hold the ALU. It starts with these ALU chips, the ALS382, and the result is always stored in the ALU register chip. The content is shown with these LEDs, and it is connected to the data bus through this bus transceivers. Those 4 multiplexers select the result, which is shown here. This is the next result with the yellow LEDs, and that goes to the register. This is the flag area. The current state of the flag is shown with these blue LEDs, and the flags are stored here, and with this bus transceivers the flags can be shown to the bus. Okay, this concludes my video about the ALU and registers of my CPU build. As always, feel free to comment. Thanks for watching, and maybe see you soon. Bye.